Welcome. In this lecture, I'm going to talk about flow performance of electrical submersible pump. So the operational map of an electric submersible pump is shown here to the left. It depicts the relationship between the delta P the pump can provide and the rate, local rate at the inlet. So it should be usually the pump handles liquid, so this should be the total liquid rate. So if I have oil and water, then here I have to put the two rates of oil and water. So relationship looks like that. And you can think of it like I have limited energy available, and that energy I can use in two ways. I can either use a very low rate, but then I can reach a very high delta P, or I can process a very high rate, but then I will be able to reach very little delta P. This collection of points, these are measured at a fixed rotational speed or frequency, typically maybe between 30 and 70 Hertz, but this is for a fixed frequency. So this curve is made using a bench test, typically reported for one stage. So that means diffuser and impeller. Typically, I change the delta P that the pump has to provide by using a valve at the discharge. I close the valve and then I get different delta P's that you have to provide, and then I map each point. I record each point, and I have a series of discrete points to define the curve. This typically is made at the reference frequency of 50 Hertz or 60 Hertz, depending where you are in the world. And this is typically measured for water. But in most cases, what you use is not delta P versus Q. You don't use a performance curve that is made on the delta P versus Q. What you use is something called head. So this head can be expressed using the symbol delta H, or I can also use simply H. And the definition of H, the head, is delta P divided by the density of the fluid times G. So it's simply scaling down. If you were going to plot the head, the performance curve using head, what you find out is that you simply have the same behavior but scaled down. And the reason to use head is that this curve is not affected by the density of the fluid. So if you have a fluid, for example, you have an oil which has less density than water, both of them are going to have the same curve. And then to calculate the delta P that is going to provide, you simply multiply the head times the density of the fluid times G. Okay. However, this curve is actually affected by the viscosity of the fluid. Okay. And if the density of the viscosity of the fluid is similar to the viscosity of the water, that means 1 centipoise for which the curve was derived. So then you can use the same curve. But if the density is very different, is much higher, then the curve will be affected and it has to change. It will change due to the effect of viscosity. Many oils that we have that are producing in oil and gas wells fields, the viscosity is high, but this is at standard conditions. When you go to a high temperature, typically the viscosity can be quite low. So 1 centipoise, 1.3, maybe 3 centipoise. And because of that, this curve, so in many cases, I could still use the curve of water. Instead of working with the collection of discrete points, the pairs of delta P and Q, instead of using that as a table, we have a table with a few points in Q1, Q2, Q3. Instead of using that, what I try to do is to use an equation to fit those points, to fit an equation that passes through those points. So a typical choice is to use a polynomial type of equation. So delta H is A times Q. If I use an order 2 polynomial, it will be something like that. Okay, but I cannot for ESPs. Second order is not enough, so I need to increase the order to 3, maybe 4 to achieve a good match. So what I do is I have the points and I try to change the coefficients A, B, and C until I match my curve. Passes through most of the points. Here also take into account that this C is actually this intersection point, the point where the Q is 0. That will be my C. Okay, so a pump is made typically of many different stages. It's not made of only one, but typically have many stages. So what you have, let's say here we have 1, 2, and 3. So what is common for all of these stages is that the mass flow is constant, or the mass flow is the same, what goes through all of these stages. And then the conditions at the suction of 1, the suction of, the discharge of 1 is going to be the suction of 2 and so forth. Okay, so that means that the delta P of the pump is going to be the sum of all the stages from 1 to the number of stages that I have of the delta P of the stage. Now, if all the stages, we assume that all the stages behave the same way, then we can say that this is going to be simply the number of stages times the delta P of one stage. Okay, simply, if I were going to draw this, let's say the delta P or the delta H of the pump versus Q, if I have for one stage, maybe it looks something like this. Okay, this is for one stage. And then for two stages, if I say that the two stages, they operate in the same way, then I simply double that, double this value over here, double this value, something like that. And this will be for two stages. Okay. Now there are a few things that we should take into account also before making this approximation. Okay, one thing is that the rate of the local rate, let's say we're producing only oil, so what is going to be the same for all stages is the QO, the standard condition rate. But the QO local, which is the one that I need for every stage, is going to be the QO times the BO at the inlet of the stage. So it's at the end pressure inlet to the stage and the temperature inlet to the stage. Okay, so it might be that for each stage the local rate might be slightly different. For the first stages or for the stages that are quite close, this BO is not going to change much. But as I increase the pressure and then this BO starts to change dramatically, then it might be that the rate through each stage is not exactly constant, but is changing slightly. Okay. Another thing could be that I'm not using the stages, they are not identical. So I might have a impeller, typically impellers that are using at the inlet, they are more tolerant to gas, so they might have a slightly different performance than the rest of the impellers. So in that case, it's not good to make simply n times the number of stages, but then I have to do a sum like here, because every stage is slightly different. When even if the stages are identical, typically because I have that the fluid is exiting one stage and entering another stage, and that process is repeated several times. I might have like maybe 50 to 100 stages in one pump, maybe more than 100, maybe less than 50, but it's around maybe that range. And what happens is that due to this exit of one stage and then entering the next stage, then I'm losing a lot of energy. So for those cases, sometimes this is not additive. It's not simply a proportional constant, but then I have some losses due to this friction and due to the change in direction. You have recirculation. So because of that, you typically have here a factor that is called the pancake factor. And this pancake factor is typically less than 1. Because it represents that it's not simply proportional, it's not adding stages together, but it's having some losses. Okay, so please take into account this is the approach is typically used, simply the number of stages, if all of them are identical. Sometimes this loss factor is included, but sometimes the stages can be different, and then I have to add all of them up. And then if I have a change in the local rate throughout the pump, that sometimes has to be taken into account. Just to have an idea, the values of delta H for one stage might be in the order of maybe 3 meters, maybe 1.5, maybe 4 meters, but for the whole pump might be something more in the hundreds of meters or thousands of meters. Okay, so let's talk now about, yeah, we looked at the curve now, how it looks like if we have a fixed frequency, but what happens if I'm changing the frequency? And why do I need to change the frequency? So let's remember our well configuration with well layout that we have here. We have a vertical well producing straight to a separator. We have no wellhead choke, and the pump, the ESP, is screwed at the bottom of the tubing, very close to the formation. So we're going to plot here is the pressure available as seen from the formation. That is the IPR, inflow performance relationship. And it tells you what pressure you need to put there to get several different rates. So that has this linear trend you see there. Okay, and now you see the pressure that is required at the exit, at the discharge of the pump to flow against separator pressure. And this is the red curve that is shown here. And that is for a constant wellhead pressure. So you see that if you want this is the rate at which the system will operate if you had no pump. But if you want to produce a higher rate, then you have to apply this delta P through the pump. Okay, typically when we have depletion, then the IPR is being reduced, is being scaled down, and because of that, the delta P of the pump usually has to increase if I have no pressure maintenance measure. Okay, if the reservoir pressure is reducing, like is shown here on that chart. So you're going to make a plot of the delta P of the ESP versus the standard conditions rate. And I might say if the rate QO is constant for these 3 years, or for a few years, T1, T2, and T3. Okay, this is with depletion. It might look something like that. Okay, now this is almost the same plot of pump performance, but the plot of pump performance is made in terms of the local rate at the inlet of the pump. So now we have to make a transformation. Essentially, we have to, one of the axes, we have to multiply by, we have to plot the QO, the local, and that is equal to the QO, the standard, times BO, evaluated at the P at the suction and the T at the suction. Okay, so it's very similar. The plot is maybe the points will be slightly not on the same line, but might be a bit to the right or a bit to the left because the suction pressure might change, especially the suction pressure might change throughout all of these years, but it still will be, fairly falling through a fairly vertical line. Okay, T1, T2, and T3. Now on this plot we can put the curve of the pump. Now it has to be the whole pump, not only one stage, because the whole pump is what is being used to bridge that delta P. Okay, let's say we have one frequency, so then it does something like that. Let's say it does something like that. And you see that this pump actually will be good to operate for this year because the curve passes through the point. So in this case, it is possible if you want to produce that rate and that delta P to use the pump. But now for year 1 and year 3, you see that it doesn't pass through the point. The performance curve doesn't pass through the point. That means that it won't be possible for the pump to produce this rate with that delta P or this rate with that delta P. I will have to change the pump, go there and change the pump and use a model that works. Usually changing pump is a very expensive process. I don't want to do it unless it's strictly necessary. And for that, typically so to change the performance map, what I use is I change the frequency of the pump. By changing the frequency of the pump, I get something like that. Q and delta H. So this is for one frequency. If I increase the frequency, I have something like this happens. And if I reduce the frequency, something like that happens. So I have F1, F2, F3, and F4. And here F4 is greater than F3, that is greater than F2, greater than F1. So it kind of makes sense. When you increase the frequency, you scale up the curve. And when you reduce the frequency, you scale down the curve. And by doing that, well, now I can allow that my performance map actually passes exactly through the point that I want. Okay, even if I change the rate, I can have a lot of flexibility in operation. We're going to see this is not the whole map. We have a few things that affect this map, but we're going to talk about that later. So how do I find the new curve having one curve? How do I find the new curve for a new frequency? For doing that, I use this method, which is called affinity loss or similarity loss. And it's a scaling principle. It's saying that I should scale rate and I should scale head with the frequency. And rate I should scale with simply linearly with the frequency. Here the frequency is expressed in terms of n. Okay, this is because they're not using electrical frequency, but they're using a rotational speed, RPM. So people sometimes use n. Okay, but it's essentially the same f. So I scale the rates with the frequency, and I also scale the head with the frequency, but squared. Okay, so let's see how that's done. So let's assume I have my curve that was measured for a reference frequency. So let's say I have 3 points here. Okay, this is Q and this is delta H. And these points that I have here, okay, let's say that this is point 1 and this is point 2, this is point 3, and here I have a Q1 and here I have a delta H of 1. And these were made, all were made for a reference frequency. Okay, if I want to find now at that point, number 1, we'll have equivalent point at a higher frequency. And that comes given by the relationship that delta H1 divided by my new delta H, let's call it 1 prime, is going to be equal to F reference divided by F, the new F, this to the power of 2. Okay, that's the relationship between the Y value of the old point and the Y value of the new point. Is going to be related, has a ratio between frequencies. The reference frequency, that's the frequency at which this delta H was measured, and this is the new frequency for which I want to calculate the new delta 1 star. Okay, so this gives that my delta H at 1 star is going to be equal to delta H1 times F divided by F reference, and all of this squared. Okay, so that tells you if F is greater than F reference, then my new delta H of 1 star is going to be higher than the original. So let's say some value up here. Okay, it's going to be higher. So that's where this line on which the delta H1 star will lay. Okay. However, if the F here is lower than the reference, that means that the delta H now 1 star is going to be below the delta H1. Okay, so then might lie down here. Okay, let's assume that F is greater than F reference, just for this example. And then that's not everything, but now I have to scale the rate, and the rate is Q1 divided by Q1 star of the new point. Then that has to be scaled by F reference divided by F without squaring. So that tells you that the Q1 star, the X of the new point, is going to be equal to the X of the old point times F divided by F reference. And here exactly the same thing. If F is greater than the reference frequency, then the Q of the new point, of the converted point, will be higher than the Q of the old point. But if F is less, then the Q will be less than the new point. Okay, so that makes than the old point. Then that makes something like that. And it tells you that this is where 1 prime is going to be. It's another point that I calculate due to the increase in frequency. The same thing happens with 2. The same thing happens with 3. These all of them are prime. Okay, and then you have a new curve of the pump that passes through these points. Okay, well the curve for the reference frequency does something like this. Okay, that's very nice, but then what we could think of is we have a collection, a table that has for the reference, and we have Q for the reference. We have a collection of points, and for when we calculate for another F, then we calculate now a new table that is not for the reference, and I convert each one of those points. But this process is actually quite manual, and then if I were using here an equation, a polynomial, like something like AQ squared plus BQ plus C, then I will have to have these new points and then create a new polynomial, which might not be very practical. So I can apply this correction directly on the polynomial. And for that, let's apply, first put the equation, delta H. This will be for all the reference points, because this I have found this tuned equation for all my reference points. Then I have here A times Q. This will be the Q reference squared plus b q reference plus c. Then I know that the q reference divided by q is going to be equal to f reference divided by f. Okay, so then I substitute that into q reference in this equation. And you end up with that expression. So now if you see, if now we use the reference, the frequency is equal to the reference frequency, this one will be 1, this term will be 1, and I end up that simplifying the original equation. No problem there. Okay, but I have one more thing to change, which is the delta H. I want to calculate the actual delta H, and I know this one is delta H of the reference times F divided by A F of the reference squared. And then I can substitute that, substitute the expression here, here, okay, and I end up with A times Q squared. This cancel out, okay, so I have nothing multiplying the first term. I have B times F divided by F reference times Q plus F divided by F reference squared times C. So that's the equation you will use to find head for a given rate, local rate at the inlet of the pump, and for a frequency which is not is different than the reference frequency. These coefficients here, A, B, and C, have been calculated for the points at reference frequency. And you see here that coincidentally the term that has the Q squared doesn't have any correction, because simply the correction with rate and the correction for head, they cancel out. But all the rest, they have a correction term. If you were using a higher order polynomial, so you will have also the correction term for all the others.